Factorial numbers are widely used in permutation combinations and various other application fields. You must have wondered if factorials of real number exist at the first place. Gamma function brings the extension of factorial function to real numbers, and beta function is closely connected to gamma function for positive real numbers. So gamma function is defined by equation 1. So gamma n is given by integral 0 to infinity e to the power minus x to the power n minus 1. Here are some important results. Gamma 1 is 1. So if I want to compute gamma 1, so this will be given by integral 0 to infinity e to the power minus x to the power 1 minus 1 dx. If I put n equal to 1 in equation 1, this gives me integral 0 to infinity e to the power minus x dx. This is nothing but minus of e to the power minus x integral 0 to infinity, which is 1. Again, gamma half is given by root pi. To prove this result, gamma half will be given by integral 0 to infinity e to the power minus x to the power minus half if I put n equal to 1 by 2 in equation 1. So if I put x equal to t square, this will imply that dx equal to 2t dt. Therefore, gamma half will be given by integral 0 to infinity e to the power minus t square into t to the power minus 1 into 2t dt. This is nothing but twice of integral 0 to infinity e to the power minus t square dt, which is nothing but 2 into root pi by 2, because integral 0 to infinity e to the power minus x square dx is given by root pi by 2. This is a standard result which we can derive using complex numbers. So gamma half is nothing but root pi, which may be written as 1.772. Next is reduction formula for gamma function. So gamma n plus 1 may be reduced in the form n gamma n. To prove this result, gamma n plus 1 is given by integral 0 to infinity e to the power minus x into x to the power n if I put n plus 1 in place of n in equation 1. So this may be expanded by parts. If I take this as first function and this as second function, integrating by parts, I get which is nothing but 0 plus n gamma n, which is n gamma n. Now why this term is 0? Because you may take it like this. Obviously this is 0 when x is 0, but when x is infinity, this may be written as xn upon e to the power x limit x tending to infinity, which is infinity by infinity form. This may be reduced by to n into x की power n minus 1 upon e to the power x limit x tending to infinity by L'Hopital's rule. And similarly, moving in this way, finally I'll be getting limit x tending to infinity 1 upon e to the power x, which is nothing but 1 by infinity, which is equivalent to 0. So hence we can say that gamma of n plus 1 is nothing but n gamma n. Now another important result, that integral of e to the power minus kx x to the power n minus 1 dx is given by gamma n upon k to the power n. This is also very important result. I'll be using this result when I'll be when I'll be relating beta function to gamma function. So let's see the proof here. So you know that gamma n is given by integral 0 to infinity e to the power minus t to the power n minus 1 dt. This may be written as 0 to integral 0 to infinity e to the power minus kx into kx n minus 1 into k dx. If I put t equal to kx, this implies that gamma n equal to k to the power n integral 0 to infinity e to the power minus kx x to the power n minus 1 dx. And this implies that integral 0 to infinity e to the power minus kx x to the power n minus 1 dx is given by gamma n upon k to the power n. So now let's see how gamma function behaves when n is a positive integer. So gamma n plus 1 is given by n gamma n. We have already proved this result by reduction formula here. So when n is a positive integer, you may reduce it gradually like this, and similarly next term will be likewise. If you go on, finally you will be left with an expression of the form this, which is nothing but factorial n. So gamma n plus 1 is nothing but factorial n. So if I say कि what is gamma 5, so this will be nothing but factorial 4. 4 factorial. So as I said in the starting, like gamma function can be defined for some real numbers too. So what happens when n is a positive rational number? So again in this case, you may write gamma n equal to n into n minus, it is n minus 1 into n minus 2 up to a positive number in gamma function. For example, if I want to evaluate gamma 7 by 2, I'll be writing it as 5 by 2 into 3 by 2 into 1 by 2 into gamma 1 by 2, and gamma 1 by 2 is nothing but root pi, you know. So finally this comes out to be 15 root pi upon 8. We may put the value of root pi to get our final result. And similarly, suppose I want to evaluate gamma 15 by 4. So this will be nothing but 11 by 4 into 7 by 4 into 3 by 4 into gamma 3 by 4. Now value of gamma 3 by 4 can be obtained from the table of gamma function. You are having a table of gamma function where we are having all the values between 0 to 1. So we'll be trying to get the values of higher numbers within the range 0 to 1, so that we can find our final value from that table, right? So what happens when n is a negative rational number? This is very important case. When n is a negative rational number, as I said here, we are having a table of gamma function within the range 0 to 1. So when I am having a negative number, so it lies almost here in the table. So I'll be trying to increase this number so that I get a value between 0 to 1. So I am rewriting this reduction formula in this form. I'll be again increasing it till I reach in this interval. So I may rewrite it like this. I'm multiplying and dividing by n plus 1. So this is nothing but gamma n plus 2 upon n into n plus 1. Similarly, this is nothing but gamma n plus 3 upon n into n plus 1 into n plus 2. And going in this manner, I can write it like this: gamma n plus k plus 1 upon n into n plus 1 up till n plus k. You may notice here that you are having k plus 1 terms in the denominator. Total number of terms in the denominator are k plus 1. Where what is k? K is the least positive integer such that it is greater than 0. Such that this expression n plus k plus 1 is greater than 0. So see an example. Suppose I want to evaluate gamma of minus 2.5. So I'll be writing it like plus k plus 1 upon minus 2.5 minus 1.5 up till minus 2.5 plus k. You may notice that this number will be the last negative number of the series. Like if I add one more term here, that will be a positive number in the denominator, and I just want negative numbers in the denominator. So here k is nothing but, k may be determined using this expression, plus k plus 1 is greater than 0. This implies that k is greater than 1.5, and this implies that k is equal to 2, because k is the least positive integer such that this expression is greater than 0. So therefore, your gamma of minus 2.5 is gamma of minus 2.5 plus 3, because k is 2, so k plus 1 comes out to be 3 upon minus 2.5. Clearly you are having 3 terms in the denominator now, minus 1.5 minus 0.5. Clearly if I add one more term, it will be plus 0.5, and I already told you should have always have all negative numbers in the denominator. So this is gamma of 0.5 upon minus 2.5 into minus 1.5 into minus 0.5, which is nothing but root pi upon denominator, whatever it is. Again, see another example. Suppose you want to evaluate gamma of minus 3.4. So this will be given by gamma of minus 3.4 plus k plus 1 upon minus 3.4. You can start writing this term up till the last negative number, minus 1.4 minus 0.4. And if I add another term in the denominator, it will be a positive number. So I will stop here. Such that minus 3.4 plus k plus 1 is greater than 0, implies that k is greater than 2.4, implies that k equal to 3. So this comes out to be then gamma of minus 3.4 plus 4 upon denominator, which is nothing but gamma of 0.6 upon denominator. So this number gamma of 0.6 may be evaluated using tables. I told you that you are having a table of gamma numbers between 0 to 1. Now, what happens if gamma n, here n is 0 or a negative number? This is an interesting case. So gamma n is not defined when n is 0 or a negative integer. Why? So you may see that gamma n is nothing but gamma n plus k plus 1 upon n into n plus 1 up till n plus k. So for n equal to 0, minus 1, minus 2, etc., what will happen? For all these n, you will be having a 0 in the denominator. How? For example, I want to evaluate gamma 0. So this will come out to be gamma 0 plus k plus 1 upon 0 into 1 up till 0 plus k, which is not defined. Similarly, if you want to evaluate gamma minus 1, this will be gamma of minus 1 plus k plus 1 upon minus 1 into 0. So you will always have a 0 in the denominator whenever you try to evaluate gamma function for a negative integer. So gamma function is not defined when n is a 0 or a negative integer. Now see some examples. Suppose you want to evaluate integral e to the power minus root x, x to the power 1 by 4 dx in terms of gamma function. So let me define my gamma function as integral 0 to infinity e to the power minus t into t to the power n minus 1 dt. So if you compare this expression with 1, you may well see that I need to put t equal to root x in 1. So my gamma n will be defined by then integral 0 to infinity e to the power minus root x into x to the power n by 2 minus half into 1 by 2 x to the power minus 1 by 2 dx, because here dt will be nothing but 1 upon 2 root x dx. So again comparing this term with our expression, so I need to put n by 2 minus half equal to 1 by 4 implies that n equal to 5 by 2. So using n equal to 5 by 2 here into, I get gamma 5 by 2 equal to 1 by 2 integral 0 to infinity e to the power minus root x to the power 1 by 4 dx. And this implies that integral 0 to infinity e to the power minus root x into x to the power 1 by 4 dx is nothing but 2 gamma 5 by 2, which may be written as 2 into 3 by 2 into 1 by 2 gamma half, which is 3 root pi by 2. Again, to evaluate this expression, if I just compare this expression with 1, so your 1 was gamma n equal to integral 0 to infinity e की power minus t to the power n minus 1 dt. This was your equation 1. So if you just compare this expression with 1, you may well see that you need to put log 1 by x equal to t. So if I put t equal to log 1 by x in 1, this will imply that minus t equal to log x, and this will imply that e to the power minus t equal to x, and also dt equal to, from this expression, equal to minus 1 by x log x. Also, when t tends to 0, x will tend to 1, and when t tends to infinity, x will tend to 0. Therefore, using these values in 1, in this equation 1, so I will be getting gamma n equal to integral 1 to 0 x into log 1 by x to the power n minus 1 into minus 1 upon x dx, which may be rewritten in this form. This minus I have adjusted in the limits, I have interchanged the limits, so it is log 1 by x to the power n minus 1 dx. This x cancels with this. So this expression is nothing but gamma n only using this result. So now I come to beta function. So beta mn is defined by this expression. As I already mentioned that these mn are taken as positive. So beta mn is defined by integral 0 to 1 x to the power m minus 1 into 1 minus x to the power n minus 1 dx for mn greater than 0. So first result is that beta function is symmetric. That is, beta mn is same as beta nm. How? So we have beta mn equal to integral 0 to 1 x to the power m minus 1 into 1 minus x to the power n minus 1 dx. By definition, this may be written as integral 0 to 1 1 minus x to the power m minus 1 into 1 minus x to the power n minus 1 dx. Why? Because by the properties of definite integrals, you know that integral 0 to a fx dx is same as integral 0 to a f of a minus x dx. So therefore this comes out to be integral 0 to 1 x to the power n minus 1 into 1 minus x to the power m minus 1 dx, which is same as beta nm. So this proves symmetry of beta function. Now here is another definition for beta function. So to prove this result, let me take beta mn equal to integral 0 to 1 t to the power m minus 1 1 minus t to the power n minus 1 dt. You know that variable of integration is dummy in case of definite integrals, because integral, if you take integral of 1 to suppose 0 to 1 x dx, this will be same as integral 0 to 1 t dt. So variable of integration is dummy in case of definite integrals. So to get this expression from my definition given by equation 1, let me put t equal to x upon 1 plus x in 1. This will imply that dt equal to 1 upon 1 plus x square dx. Also when t equal to 0, x equal to 0, and when t equal to 1, then x tends to infinity. Why? Sorry. Because t is given by this expression implies x equal to t upon 1 minus t. So when you put t equal to 1, you get an expression of the form 1 upon 0, which is infinity. So beta mn, substituting these values in expression 1, this implies that beta mn is given by integral 0 to infinity x upon 1 plus x to the power m minus 1 into 1 minus, because t equal to x upon 1 plus x, into 1 upon 1 plus x square dx. Now this is equal to integral 0 to infinity x upon 1 plus x to the power m minus 1 into I think this has changed a bit. Let me rewrite it. So substituting these values in expression 1 I get beta mn equal to integral 0 to infinity x upon 1 plus x to the power m minus 1 into 1 minus x upon 1 plus x to the power n minus 1 into 1 upon 1 plus x square dx. This is same as integral 0 to infinity x upon 1 plus x to the power m minus 1 into 1 upon 1 plus x to the power n minus 1 into 1 upon 1 plus x whole square dx. And this is same as integral 0 to infinity x to the power m minus 1 upon 1 plus x. Here the power is m minus 1, so it is m minus 1, it is plus n minus 1 and 2 here. Which is nothing but integral 0 to infinity x to the power m minus 1 upon 1 plus x to the power m plus n dx. So here is another form of beta function, that beta mn is twice integral 0 to pi by 2 sine 2m minus 1 theta cos 2n minus 1 theta d theta. To prove this result, we know that beta mn is given by integral 0 to 1 x to the power m minus 1 into 1 minus x to the power n minus 1 dx. So if I put x equal to sine square theta, this will imply that dx is 2 sine theta cos theta d theta. Using these values, here I get beta mn equal to integral 0 to pi by 2 sine 2m minus 2 theta into cos 2n minus 2 theta into 2 sine theta cos theta d theta. Also limits change when you put x equal to 0, your theta is 0, and when x equal to 1, your theta is pi by 2. So this is same as beta mn equal to 2 integral 0 to pi by 2 sine 2m minus 1 theta into cos 2n minus 1 theta d theta. Now a very important result which gives you relation between beta gamma functions, and this is of utmost importance in your syllabus. To prove this result, I will recall a relation from gamma function which I told you, that integral of 0 to infinity e to the power minus kx into x to the power m minus 1 dx is given by gamma n upon k to the power m. I proved this result while doing gamma function. I am replacing k by y here. Why? Just because we are used to writing dx, dy type of terms, but dk is not very common. So because I'll be just having a term dk or so I will be preferring to have dy instead of dk. So this will imply that gamma m upon y to the power m is given by integral 0 to infinity e to the power minus x to the power m minus 1 dx. And this implies that gamma m is nothing but e to the power minus yx y to the power m into x to the power m minus 1 dx. I am now multiplying both sides with e to the power minus y into y to the power n minus 1. You will just understand the reason, because I am trying to make this numerator gamma n into gamma n. So to make it gamma n, I'm multiplying by this term, and later I'll be integrating within the limit 0 to infinity. So this will be given by integral 0 to infinity e to the power minus y 1 plus x y to the power m plus n minus 1 x to the power m minus 1 dx. Hope you understand that I can take this y terms inside these integrals, because I am integrating with respect to x. So y just acts as a constant here. So I may write it outside this integral or inside, it's one and the same thing. So this implies that gamma n I may take out, and now I am integrating both sides with respect to y within the limit 0 to infinity. So gamma m into integral 0 to infinity e to the power minus y to the power n minus 1 dy is given by integral 0 to infinity double integral here e to the power minus y 1 plus x y to the power m plus n minus 1 x to the power m minus 1 dx dy. And you may see that this is nothing but gamma n. So you may rewrite this expression as gamma n into gamma n. So I just told you that I am trying to make gamma m into gamma n in the numerator. So this comes out to be then integral 0 to infinity. This expression may be written as integral 0 to infinity e to the power minus of 1 plus x into y to the power m plus n minus 1 into x to the power m minus 1 dy dx. I'm not left with any space here, so I'm just continuing here. This I'll be deleting later on. So this implies that gamma m into gamma n is given by integral 0 to infinity gamma of m plus n upon 1 plus x to the power m plus n into x to the power m minus 1 dx. This result is again using expression 1. You may see expression 1 here. So I am just having, if you compare, in place of k I am having 1 plus x, and here in place of m I am having m plus n. So using expression 1 I get this result. So just transferring gamma m plus n to left hand side, what do I get? Gamma m into gamma n upon gamma m plus n is given by integral 0 to infinity x to the power m minus 1 upon 1 plus x to the power m plus n dx. Now this is again a known result. This is the another form of beta function. I already proved it. So this is nothing but beta mn. So this gives you the relation between beta gamma function, that beta mn is nothing but gamma m into gamma n upon gamma m plus n. So this is very important from examination point of view. You must remember this derivation. So I am just deleting this now so that I may continue with my next expression. So here again I want to prove this result now. So you already know that another form of beta function was given by integral twice of integral 0 to pi by 2 sine 2m minus 1 theta into cos 2n minus 1 theta d theta. This also we did while we were taking up gamma function. Now if I just replace two m minus 1 by p and 2n minus 1 by q, that is m equal to p plus 1 by 2 and n equal to q plus 1 by 2, I get my expression. This implies that twice integral 0 to pi by 2 sine p theta cos q theta d theta is given by p plus 1 gamma of p plus 1 by 2 gamma of q plus 1 by 2 upon gamma of p plus q plus 2 by 2. If I write 2 here, I get my result. This. Now see some examples. I want to evaluate this result. So integral of 0 to pi by 2 sine cube theta sine cube x cos 5 by 2x, it may easily be written as integral in terms of gamma function. So it may be written as gamma of 3 plus 1 by 2 gamma of 5 by 2 plus 1 by 2 upon 2 gamma 3 plus 5 by 2 plus 2 upon 2. And now you may solve this to get your final result. Similarly, this integral may be rewritten as integral 0 to pi by 2 sine 1 by 2 theta into cos minus half theta plus cos minus half theta d theta. Here also you may multiply it by sine 0 theta and apply the same result here, that this integral 0 to pi by 2 sine p theta cos q theta d theta is given by this. And you may just get the final expression for this. Now here is another important type, that beta m plus beta mn is given by this. I always prefer to solve these types of question using beta gamma relation. So taking up right hand side, I get it is gamma m plus 1 into gamma n upon gamma m plus n plus 1 using beta gamma relation plus gamma m into gamma n plus 1 upon gamma m plus n plus 1. So denominator is common. So I am writing this as m gamma m, and similarly I am writing this term as n gamma n. So this may be written in the form, you may take gamma m, gamma n out, so m plus n inside, and this also you may write it as m plus n, gamma m plus n. So this cancels, and this is nothing but beta mn. So again, the examples of this kind. So you know that beta function, suppose I want to prove one, I'm just giving you the hint and you may solve it yourself. Like you know that beta mn is given by integral 0 to 1 x की power m 1 minus, or you may take it in the form of t. So t to the power n 1 minus t to the power m minus 1, it is 1 minus t to the power n minus 1 dt. So clearly you what do you need to do in this case? You just need to put t equal to x square. So if you put x square equal to t, you may get your final result. Similarly here, you may rewrite this as integral 0 to 1 x square into 1 minus x5 to the power minus half. So you to manage this result, you need to put x5 equal to t. So you will finally get an expression in the form of beta gamma functions. For details of these questions, you may go to my website, theengineeringmaths.com. theengineeringmaths.com. So this is all for beta gamma function. See you in the next topic in my next class. Thank you so much.